My name's Oliver Rue. I'm a software engineer at Bloomberg in New York City, and I'm here today to talk to you about building robust embedded systems. Whether you want to build better home automation or the next Mars rover, I hope what we discuss today will help you build resilient software wherever it runs. But because it's 2025, a quick heads up before we dive in. Much of the artwork that you see in this talk was generated with AI tools. While I'm a pretty good coder, I'm a terrible artist. But with that said, all of the writing, including what I'm saying right now, is entirely my own. Now with that out of the way, to get started, we should probably try to better understand what an embedded system actually is. Formal definitions of embedded systems will say something like this: a microprocessor system built to perform a dedicated function. That's a good definition and still very applicable. However, for the purposes of this talk, I actually like this comment on a Reddit thread regarding the definition of an embedded system. Vidicon31 says, "I feel like it kind of depends on who you ask, but I would say that an embedded system is a device that contains a computer that the average person would not consider being a computer." And in this case, a computer would be a general purpose system built to perform a range of different functions. And by his logic, his or her logic, an embedded system is anything that the average person wouldn't consider one of these. So, a microwave, not a computer. A car is not a computer. And a thermostat is not a computer. And in the past, internally, each of these things would look quite different from a computer as well. They'd likely run on some constrained microcontroller or microprocessor and might only ever run one version of software, usually called firmware for that reason. But today, things have changed. The internet is everywhere now, and compute power is laughably cheap. So today we have the Internet of Things. Our cars are lousy with touchscreens, and you can play Doom on your smart fridge. While still not operated like a computer, internally, many of today's embedded devices look a lot more like your PC. Your smartwatch, smart refrigerator, or smart thermostat are likely running an operating system very similar to your laptop or server. And if you run Linux, they might be the same. These sorts of embedded devices, the ones running a modern OS on modern hardware, are what I want to discuss today. Because these devices are not operated like modern computers, but have modern computers at their core, building and deploying them introduces a bunch of interesting hardware and software problems. And we should talk about a couple of them. Regardless of the device, it will need to be powered in some way. And the first issue we run into with power is availability. Anyone who's dealt with a flaky smart device will know that the #1 way to fix it is to simply turn it off and on again. However, modern operating systems don't always appreciate unexpected power loss. And even if the OS is okay, your software may not handle that well either. Beyond that, power consumption is another problem. Many embedded systems run on batteries, but even a modest embedded CPU can draw significant amounts of power. It's even a good idea for wall-powered devices to think about consumption as well. Our smart home devices might only draw a couple watts, but they can run all day long for years, which can quickly add up. Now let's talk about the basic building blocks of a modern computer system: CPU, RAM, and disk, also known as persistent or non-volatile storage. Modern operating systems are great at abstracting away the physical details of the underlying machine. However, while your code might appear to run the same on an embedded system, you can quickly run into issues if you expect the same performance as your typical desktop or server. Other than limited resources, CPU and RAM should be fairly transparent to the embedded programmer, but non-volatile storage can take special considerations. More often than not, An embedded OS is using some form of flash memory as its non-volatile storage. And as you may know, flash memory has a finite number of write cycles. So while it may not appear different from the OS's perspective, over the life of the device, the storage can quickly wear out, and run into issues. And this is especially relevant when the device is expected to run for years or decades and never had a lot of storage to begin with. Now let's talk about failure. While power cycling a device may be the easiest way to reset it, that doesn't really scale well. Instead, embedded software should be written in a fault-tolerant manner, always considering how to fail gracefully in every situation. Furthermore, the operating system must be properly configured to handle failure in our application as well. And if a device requires external connectivity, like Wi-Fi, Ethernet, or Bluetooth, there are even more failure modes to consider. While the low-level details of these protocols are likely taken care of by the OS, any connectivity can be very unstable, and our devices need to handle connection loss gracefully and predictably. These are indeed good considerations when designing software for any environment, but they can become even more critical when developing for an embedded system. And when there is an inevitable failure on your system, detection and debugging can be much more troublesome in an embedded environment. Logs for our desktop and cloud applications are often available in some form of logging console. But for a number of reasons, like connectivity, data usage, and storage, accessing logs on an embedded system can be much more difficult. Also, we must thoughtfully consider how our devices represent their current state to users, because they likely have limited methods of communication in that way. Beyond operation, your device likely requires specific configuration. Wi-Fi passwords, IP addresses, host names, application config, and much more need to be loaded onto your device for it to operate. We take for granted how easy this is on our PCs. But embedded device likely does not have the luxury of a monitor, keyboard, or mouse, and might not be located in an easily accessible place. And this process becomes even more cumbersome if you're managing a fleet of devices or your configuration needs to change over time. Another huge configuration concern is security. Embedded devices share all the same security concerns as other computer systems, but the risk can be exacerbated by poor or lacking configuration. There have been numerous well-publicized examples of embedded devices being compromised by old security vulnerabilities or simply default passwords. On top of that, physically remote devices are easier for bad actors to access and put your data at risk. And in the event of a vulnerability or your software changes, you need to find a way to deploy it. Deployment mechanisms for software are already numerous and complex. Add in the issues of fault tolerance that we just discussed, and this process becomes even more difficult and risky in an embedded environment. Now that we've touched on some high-level issues with embedded systems, let's go into a bit more detail and discuss some strategies to solve them. By no means will this be a comprehensive guide to building reliable embedded devices. By definition, embedded devices are usually designed with a specific function in mind. So every use case will have specific requirements. And this is a good time to mention that the title of my talk is a bit misleading. Little of this is specific to Python, and instead it can apply to any software you want to run on an embedded operating system. Nonetheless, I hope what we discussed today gives you some useful insights into your next design. To start, let's talk a little more about storage. Before we can talk about solving issues with embedded storage, we need to discuss some of the problems in a little more detail. As mentioned before, the software in your embedded system the storage on your embedded device will likely be some form of flash memory, like an SD card or eMMC. These devices are great. They're plentiful, cheap, and easy to use. However, they have a tendency to wear out over time if we aren't careful. The best way to avoid this is to thoughtfully consider how and when we write to persistent storage. One great example of this is application logging. We all love to litter print statements throughout our code. But if every one of these print statements ultimately ends up on your small flash storage, you can quickly run into issues. And the same is true for OS logs. This may seem like a simple problem to fix, but even the pros have made this mistake. Famously, in 2021, Tesla had to recall over 100,000 vehicles because of their onboard eMMCs were failing. The culprit? It appears significant application logs were written directly to storage, shortening their lifespan and ultimately causing failure. Another peril with storage, which relates to our issues with power and fault tolerance, is the danger of corruption when the power unexpectedly fails. Flash storage devices are complicated at a low level, and interrupting a flash operation can potentially corrupt a large block of your storage, jeopardizing the device as a whole. If you've used a Raspberry Pi, you may have heard of this before. This issue plagued the Raspberry Pi community for years, causing regular corruption and data loss. And while multiple factors were at play, unexpected power loss, insufficient power supplies, and low-quality SD cards were the main suspects. And beyond the low-level hardware, your embedded software needs to handle power loss as well. What if you lose power while in the middle of writing the main config file for your application? Simple problems like this could easily brick your device. There are many solutions to flash storage wear corruption, but my favorite is to simply avoid disk writes altogether by making your file system read-only. This is likely what many of your embedded devices already do, and it's the reason you can yank the power on your Wi-Fi router and it's no worse for wear. There are many ways to accomplish this, and it usually depends on your OS and hardware. For example, on the well-known Raspberry Pi, they make this super easy with something called an overlay file system, which is a feature that makes your file system read-only while appearing to make it writable to applications, except all writes are temporary and are only stored in RAM. And if a full read-only file system is not an option, another good strategy is to send noisy disk writes like OS logs to a temporary RAM-based file system while writing important, less frequently changing data to your persistent storage. Read-only or RAM-based file systems are great, but this strategy does have its drawbacks. Related to what we discussed about debugging, if you're sending your logs directly to RAM and your device loses power, all your logs are lost, and that can make it very difficult to diagnose issues. You should also consider mitigating storage and power loss issues at the application level. One of the best ways to do this is to simply use libraries that handle interruptions for you. When properly configured, file-based databases like SQLite usually include multiple protections against data loss in the case of unexpected interruption. Even simpler, if you want to avoid corruption while modifying files from your application, I usually do something like this. Read the existing file, make your changes, write the new file contents to a temporary file, and finally, rename that temporary file to the original file name. At least on Linux, file renames are generally considered atomic. So if you were to lose power during this operation, on restart, your application would either see the old or the new file, but nothing in between. And now let's talk about fault tolerance, a huge topic in itself, and not just relevant to embedded environments. It's always a good idea to develop our software to proactively handle any errors it encounters. As always, it's application specific, but here are a couple basic design patterns for you to consider. To start, let's discuss process managers. Because we're concentrating on embedded devices running on an operating system, it'll be the operating system's job to start and manage our software processes over time. However, modern operating systems are complex and offer a number of different ways to manage an application. You can use init, systemd, OpenRC, supervisord, Docker Compose, and many others. And your choice is probably application dependent, but my advice would just be to pick one and learn how to use it properly. Don't try to roll your own unless you really know what you're doing. I often pick systemd, mostly because I know it and it's available on most of the systems I use. Systemd has a million different options, but most applications can run forever with just a simple config. This config file tells Systemd how and where to start our application, when to start it, and what to do when it unexpectedly fails. With just this, you can enable your software, your service, and know that Systemd will take care of managing it forever. Now let's talk automatic fault recovery. While PCs and servers likely have UIs or consoles to reset them in case of error, embedded systems may not share this luxury. One simple pattern I like is that of a watchdog. In its broadest form, a watchdog is a mechanism that monitors your system for abnormalities and automatically takes corrective action. Often, that monitoring is just checking for responsiveness or connectivity, and the corrective action is simply a software reset or system restart. It might not be possible to foresee every way that your software can fail, but if you can find some basic conditions that define the liveness of your software, you can have a relatively simple watchdog, monitor those conditions, and reset it if necessary. Now let's talk about fault tolerance and configuration. One of the riskiest times for our devices is during updates or configuration changes. Say you have a remote, inaccessible network device and you need to change its Wi-Fi settings. What if you send the wrong password? Or what if the new Wi-Fi network isn't available? For an inaccessible device, this could effectively kill it. When we build configuration mechanisms, it's always good to consider what could happen if you push a bad configuration and include some sort of fallback mechanism or at least some way to alert on it. Depending on your needs, there are many more strategies when designing for fault tolerance, and I'd love to discuss them after the talk. Regardless of how fault tolerant we make our embedded devices, they will always find new and creative ways to fail. When this happens, it's important that we have systems in place to monitor and diagnose those issues, let alone ways to fix them. For a lot of my home projects, my main technique for monitoring debugging is simply logging in via SSH and reading the logs. This can be fine for a small number of pet projects on your home network, but it's not advisable or sustainable for anything more. Logs and metrics are likely our first instinct when debugging issues with our software, but as we've already mentioned, saving logs directly to device storage is not always advisable, and only storing them in RAM leaves you blind in the case of power loss. One logical solution is to send the logs and metrics somewhere else where they can be safely stored and analyzed. There are many good open source options for sending this data and a ton of cloud-based solutions for collecting and analyzing them, including many with generous free tier options. The monitoring solutions we just discussed can work well, but they assume that the person debugging the issue will get value out of reading low-level application and OS logs. This isn't always the case. I can't think of the last time I wanted to read the logs on my toaster. Sometimes the best mechanism for communicating system state to the user is through physical feedback. Consider adding displays, lights, or sounds to your device. Something as simple as a single LED can often communicate enough information to a user to help them debug it and fix an issue. Since our embedded devices are computers but aren't operated like a computer, we should always consider more natural ways for the users to interact with them. And finally, configuration. At some point in our life, our embedded devices will need to be configured to perform the function they're designed for. However, configuration can be very complex, and there are a lot of considerations. Single-purpose devices may only need configuration once at birth. And for personal projects, there's nothing wrong with logging onto a device and running an install script. But for anything more, consider some form of automated software image building and provisioning. Not only does this ensure that the devices are configured and deployed consistently, it makes it much easier to scale. There are a couple good options for this, like Buildroot and Yocto, but all of them are too complex to get into in this talk. Many devices need to be reconfigured throughout their lifetime, And besides pet projects, manually modifying config files is not a realistic option. Instead, we should thoughtfully consider how to provide users with some form of configuration interface. Sometimes a simple on-device API that exposes common configuration parameters is sufficient. In other cases, it's better to include some form of UI. For example, most of our home Wi-Fi routers present a configuration web UI at a given address that allows us to easily configure device settings. There are many more considerations for device config that may influence your design, like potential for automation, idempotence, and fail-safes, and I'd love to discuss them after the talk. Beyond application config, our long-running devices may require software updates and security updates throughout their lives. These mechanisms are usually complex and very closely tied to the OS. The inaccessible nature of embedded devices only exacerbates this, and devices can go years without necessary security fixes. If you're doing small-time embedded work, I highly suggest choosing one user-friendly ecosystem and following their guidelines. If you're doing large-scale professional work, you have many more options with varying levels of customization and difficulty. So we've talked about a bunch of problems and solutions for today's embedded devices, but where does that leave us? Today, embedded devices are basically computers, even if we don't treat them like them. They operate much the same as modern computers and face the same challenges, but can carry a greater risk of failure. We discussed a lot of options, but by definition, embedded systems are purpose-built, so each application will be different. However, with thoughtful design, robust patterns, and a bit of paranoia, we can build devices that are resilient, secure, and easy to live with. And by embracing the constraints of embedded systems, we can learn habits that lead to more reliable software wherever it runs. That's my talk. Thank you.
Excellent. So we have some time for questions. Does anyone have any questions? Excellent. I think in the meantime, maybe you can expand on some points that you said you'd love to discuss. Feel like you wanted to get more into detail.
You're kind of putting me on the spot here. No, it would be better to discuss somewhere else, I think. I think something interesting, though, is that I followed a talk about embedded devices. But what I'm talking about is kind of uniquely different from this. Mark, right? What Mark presented on was much lower level, like running MicroPython as firmware on a microcontroller. And that's a different type of embedded system than what I'm targeting. So my talk was more about like running a full OS on an embedded device and the challenges there. There's a whole nother unique set of challenges when running on this sort of embedded device. It's often more difficult and simpler in some ways. More difficult because you don't get like the benefits of, say, the whole Linux networking stack, but simpler in that you're not running the entire wildly complex Linux kernel and you have to debug that. So I just wanted to mention that like I said, embedded systems are very application dependent, and it's a deep rabbit hole and hard to cover everything in one little talk.
Excellent. This was actually a really nice remark, for me at least. Very helpful. Okay, nice. So if we don't have any more questions, I'm sure Oliver will be happy to discuss later outside. And thank you. Excellent job.